Welcome back to Unit 7 of Chemistry Matters, where we're exploring properties of acids and bases. In the last video on our playlist, our students began testing those properties using indicators like litmus paper and cabbage juice. By now, you've been able to conduct similar tests of your own. So let's get back to our classroom to see if your results are similar to the data our students found.
Okay, since everyone's done, let's discuss your results. Team 1, tell me how the red litmus test went on your solutions.
Well, the biggest impact was the baking soda. It turned blue immediately.
I was watching you work and I was surprised by your shampoo and conditioner results. I expected them to turn the red litmus blue also. So how did you guys classify the baking soda? Acid or base?
It was definitely a base.
Well, good. What did the baking soda do to the cabbage juice color?
Well, it was kind of bluish-greenish, but the others were a range of colors from purple to red.
Excellent. That's a great descriptor too, a range. Acids and bases show a great deal of diversity and strength and can be made into various % concentrations. The amount of acid or base that's dissolved in a solution can affect the reaction it has with the indicator. For example, it's possible that the lemon juice was more acidic than the vinegar. Though they're both acids, one solution might cause a different color change than the other. So Team 2, what were your results with the blue litmus?
Well, the lemon juice and the vinegar both turned the blue litmus pink.
And it was kind of like the other teams was with the cabbage juice. There was a range of colors, but mostly a pinkish reddish mix for the acids.
So the vinegar and the lemon juice are clearly acids.
Excellent job, everyone. You correctly identified these substances. We'll get into some more depth here shortly on acids and bases, but for now, let's go over a few general properties of each type. Acids are electrolytes. As you've seen, they turn blue litmus red. They also have a sour taste, and they react with metals to form hydrogen gas. Manufacturing hydrogen for industrial purposes is usually done by reacting an acid with a metal. Some examples of acids that we encounter on a daily basis are vinegar, milk, soft drinks, apples, and citrus.
Yeah, that makes sense. I love lemons, but I still cringe a little every time I put some on my food. They're so sour.
That's right, and as you saw today, lemons are definitely acidic. So now some general properties of bases, they're also electrolytes, and as you saw, they turn red litmus blue. They have a bitter taste, and they also have a slippery feel. Some examples of bases are ammonia, lye, antacids, soap, and baking soda.
Okay, so that's what makes soap so slippery. It's a base.
Well, basically. There are actually a few different ways we can define an acid and a base. One of the most common models, and the most useful for our class, is the Bronsted-Lowry Model. Bronsted-Lowry acids are defined as substances that donate one or more protons to another substance in a solution. The Bronsted-Lowry definition of a base is any substance that can accept a proton. Look at this model of the hydrogen plus ion. What do you notice?
Since it's hydrogen, it only has one proton.
And there are no electrons. That's why it has a positive charge.
Exactly. An H+ ion is just a proton. Bronsted and Lowry knew the electrical attraction between the acid and the base causes the proton to be pulled off the acid and bonded to the base. Notice here that the water molecule has enough negative charge to pull apart the HCl. The proton is pulled away from the HCl towards the water. Can you see from this reaction why this is the acid and that's the base?
Yeah, I think I can. The water is acting as the base since it's accepting the proton. And HCl is acting as the acid since it's giving away the proton.
Exactly. Now let's look at this reaction with ammonia, NH3, and water. What's acting as the acid and what's acting as the base according to the Bronsted-Lowry model?
I say the NH3 is acting as the base because it's gaining the proton.
Wait, so that means the water is acting as an acid, right? Can it do that? Can it be both an acid and a base?
Absolutely. Well done, both of you. Yes, water can be an acid and a base. It's what's known as amphoteric, which means it acts as an acid or a base. It just depends on what other substances are present in the water. For example, if water's near HCl, like you saw before, it'll act as a base and take a proton. If it's near ammonia, it'll act as an acid and lose a proton to the NH3. In addition to the Bronsted-Lowry model, many people find the Arrhenius model useful in describing acids and bases. In the Arrhenius model, an acid is a substance that forms H+ in the water. You see here how HCl loses the H+ and that the water accepts the H+. An Arrhenius base is a substance that produces hydroxide, OH- in water. In this reaction, the sodium hydroxide in the water releases the OH- ion. The Arrhenius model is limited to acids and bases that contain hydrogen and oxygen. There's one more model of acids and bases known as the Lewis model. According to the Lewis model of acids and bases, an acid is any substance that accepts a pair of electrons. In this diagram, boron trifluoride is pulling an electron pair away from the ammonia molecule. The boron trifluoride is accepting that electron pair, so it's a Lewis acid. A Lewis base is any substance that donates an electron pair. The ammonia molecule is the electron donor because it's donating the pair of electrons into this bond. That's why we call ammonia a Lewis base. The Lewis model is very effective when studying bases and acids that do not have the H+ ion. We can use the Lewis models to describe an interesting phenomenon. I've given you both some distilled water and a pH meter, as well as a sample of metal. You've already been introduced to the pH scale. Can you tell me about it?
It measures acids and bases.
And neutral is located in the middle with a pH of 7.
An acid has a pH of between 0 and 7, and a base is between 7 and 14.
You're right. And remember, stronger bases will show up closer to 14, and stronger acids will be closer to 0. Colors like these would be seen on qualitative tests, such as pH paper or other color indicators. Rachel and Aaron, I've given you guys a sample of zinc nitrate. And Kat and Cade, you two have a sample of an aluminum nitrate. With your safety glasses on, place the pH meter into the water and measure the pH.
Our water has a pH of 7. That's what I expected.
Us too.
Now add your metals and watch the pH meter.
Wow, that's weird.
The pH dropped almost to 3 after the zinc nitrate was added.
Ours is even lower. Ours went all the way down to 2.
But how does it do that? I mean, there aren't even any hydrogens in the formula for aluminum nitrate. How is the pH going down?
Good question. This demonstration illustrates how metal cations can lower the pH of a solution. What happens is the metal cation orients itself next to the oxygen in the V-shaped water molecule. Remember from Unit 4 that water is a polar covalent compound. The shared electrons between the hydrogen and the oxygen shift towards the more positively charged metal and further away from the hydrogens. Because of this electron shifts, the hydrogen breaks apart from the water molecule, and when these hydrogens are released into the solution as hydrogen plus ions, they make the solution acidic and lower the pH. So as you can see, there are a few different ways that substances can be classified as acids or bases. It depends on the behavior of the substance we're observing. We use the model that best describes our observations. For this course, we'll focus on the Bronsted-Lowry and Arrhenius models of acids and bases. You've all done a great job so far in your investigations of acids and bases.
It looks like our students now have a much better understanding of the properties of acids and bases and the various ways we can classify them. Speaking of classifying acids and bases, there's often a misconception among beginning chemistry students regarding the terms strong and weak when describing acids and bases. It's important to note that the term strong, when referring to acids and bases, describes their ability to completely ionize in solution. Strong does not refer to how corrosive or dangerous an acid is. How dangerous an acid or base is depends on its concentration and not its description as strong or weak. Think of a molecule of acid as a great white shark. If there's one shark in the whole ocean, there's not much danger. But if there are lots and lots of great white sharks in the ocean, the concentration of sharks is now much higher and you might want to stay out of the water because there would be more danger. Being a strong or weak acid is not related to its concentration. A strong acid or base is one that's 100% ionized in water and therefore can be thought of as a strong electrolyte. There are 6 acids that are typically referred to as strong: hydrochloric, nitric, sulfuric, hydrobromic, hydroiodic, and perchloric acids. The strong bases are those that contain the alkali metal and heavier alkaline earth metal hydroxides, such as sodium hydroxide, potassium hydroxide, calcium hydroxide, and barium hydroxide. As an example, if you took 10 hydrochloric acid molecules and dropped them into water, all 10 HCl molecules would break apart and would therefore form ions in solution. So you'd have 10 H+ and 10 Cl- floating around in that solution. Since it's a strong acid, it's 100% ionized. A weak acid or base is one that does not completely ionize in solution. Therefore, weak acids and bases are known as weak electrolytes. If 100 acetic acid molecules were dropped into water, only 3 molecules would separate into 3H+ and 3 C2H3O2-, or acetate. The remaining 97 acetic acid molecules would remain as acetic acid. Examples of weak acids are hydrofluoric, acetic, phosphoric, carbonic, and hydrocyanic. The most common weak base is ammonia, NH3. When an acid and a base are brought together, a chemical reaction occurs, referred to as a neutralization reaction. You may be familiar with a neutralization reaction if you've ever heard about a hazardous materials team trying to neutralize a chemical spill on a railroad or highway. First, the hazmat team will try to identify the spilled material. If it turns out to be a base, like sodium hydroxide, the hazmat team will add an acid to neutralize the chemical. Of course, a neutralization means that an acid and base have reacted to form a salt. By salt, we mean any ionic compound that forms from the neutralization reaction between an acid and a base. The ionic salt is oftentimes aqueous, so the net ionic equation of an acid-base or neutralization reaction is H+ plus OH- yields H2O. We can also use neutralization reactions to our advantage in a chemistry lab. If neutralization is done under carefully controlled conditions, we can use a technique called titration to determine the exact concentration of unknown solutions. Titration is the analytic method in which a standard solution is used to determine the concentration of an unknown solution. How can titration be useful? Lots of people depend on the information gained by titration analysis every day. For example, titration can be used by hospitals to determine the concentration of chemicals in blood or urine. Titration is often the way we figure out the fat content or water content or the concentration of vitamins in food. Titration is the best method to determine if cheese has the right flavor chemical concentration before being distributed to grocery stores. And as you might expect, titration is necessary during the very precise manufacturing processes needed to produce medications of the proper dosage. Titration experiments can be run with acids and bases. Keep in mind that titration is tricky and requires patience. Let's say our laboratory has been given a sample of an unknown base from the site of a chemical spill. You'll be the chemist who has to figure out how concentrated it is. You'll use a special tool called a burette that's like a graduated cylinder with a dispensing tip called a stopcock. The burette will hold a known volume of a known concentration of acid, like the acetic acid in my burette. The chemical in the burette is often called the titrant. You'll carefully measure a volume of a base of unknown concentration, in this case 50 milliliters, and place the solution of base in a flask right under the burette. For this lab, we'll plan to use a neutralization reaction, allowing the acetic acid to drip very slowly into the solution of unknown concentration. But wait, we need a way to know when the mixing of acid and base has caused neutralization, called the equivalence point of the reaction. We can visualize the end point by adding a chemical indicator. The indicator, well, it indicates by changing color. Many chemical indicators exist, and they're chosen for their ability to change color at a specific pH range. You can find a list of useful chemical indicators in our Chemistry Matters toolkit. I'm using phenolphthalein. It turns pink in the presence of a base. See, it's pink. Using this burette allows us to know exactly what volume of our known acetic acid is needed to reach the end point. And the correct indicator will change color the moment you reach the equivalence point in the reaction. Once I finish neutralizing the base, I can use the burette to see how much acid I used. I'll subtract the amount of acid left in the burette from the amount I started with. Armed with the volume and concentration of our acid solution and the volume of our base solution, we can calculate the concentration of the base. Then it's time to use mathematics and computational thinking to determine the concentration of the unknown base in the beaker. That means using the titration equation shown here. The titration calculation formula is similar to the dilution equation. In the titration equation, Ma refers to the molarity of the acid. Va is the volume of the acid. Ma and Va are multiplied by the number of hydrogens found in the formula of the acid being used. For example, HCl would have a value of 1 assigned for the number of H3O+. Sulfuric acid, H2SO4, would have a value of 2. Mb refers to the molarity of the base. Vb is the volume of the base. Mb and Vb are multiplied by the number of hydroxides present in the formula of the base. For example, sodium hydroxide, NaOH, has only one hydroxide. The goal of a titration experiment is to determine the concentration of a base or acid. In this lab, you'll be solving for the concentration of the base. You'll be given an acid of known concentration to be used as the titrant. So let's head back to our classroom, where our students are using materials from our Chemistry Matters toolkit to get some hands-on practice with titrations. While you do that, I'm going to continue doing some titration work in this lab.
Okay guys, who can tell me the objective of our titration experiment today?
Well, a titration allows us to calculate the concentration of an acid or a base solution using the titration equation.
Sure, but why are we doing this lab today, besides getting some titration practice?
Oh, well, the instructions say that our lab has been sent a sample of a base called sodium hydroxide, or NaOH, from a chemical spill. And as a member of the hazmat team, our goal is to find the concentration of the base.
Exactly right. Can someone explain their setup for us? It's okay if you want to use your notes for reminders.
I'll try. So we have this burette, and we put our standard solution of acid into it.
Okay, what does that mean, standard?
That we know its concentration.
Very good. And I've already put 1 molar HCl in your burettes. So does it matter exactly how much I put in there?
No, we just need to take an accurate reading of the volume and of the solution before we start the titration. How about if we add 25 milliliters of the acid to the burette to start?
Yeah, we'll take another reading of the burette after the indicator changes colors, and the differences in the volumes will be the volume that we used in the titration.
Great. There are several different pH indicators for different labs. Since we're using a strong acid and a strong base, we're going to use phenolphthalein as the indicator. Both groups have a strong base of unknown concentration that only has one hydroxide, which means it only has one OH minus in the formula unit. Measure 25 milliliters of the sodium hydroxide of unknown concentration and put it in your Erlenmeyer flask. There's a magnetic stir bar in here, and it's on a stir plate. This ring stand is set over it so that the acid from the burette can be added into the flask. Before you do that, you're going to add 3 drops of phenolphthalein. Then you'll begin adding the acid by opening the stopcock of the burette in about 1 milliliter increments until the color change persists. The pink color is going to disappear. Once you get a light pink, you'll start adding the acid 1 drop at a time until the pink barely disappears. Once it's done, you've reached the end point. Then it will be time to determine the volume of acid that you used in your titration by subtracting your final volume of acid in the burette from the starting volume. Then you'll use that information in the titration formula to calculate the molarity of the base. Does anyone have any questions? I know that was a lot of information, but you have your instructions to guide you. When you finish, you're going to put your work on a whiteboard so we can see your calculations.
While our students get started on their titration labs, we'll let you do the same thing. Work with your teacher to make sure you're following good lab practices and safety procedures, and carefully log your results so you're able to argue from evidence when analyzing your data. When you're done, I'll see you at the top of the next video on the playlist.